because this is
Okay,
new
sir.
topic. So
Okay,
earlier
sir.
I have never talked about this. So I want that because I have got a hobby of uploading the video.
Okay, sir. We are recording, sir. We are recording.
Yes, yes, we will record and the recording you will send to me by mail. I will give you my Gmail account. So at Gmail it will be coming. So
Yes, sir.
no
Yes,
problem.
sir.
So I
Yes, sir.
will be speaking exactly after 5 minutes.
Okay, sir. Okay, sir.
So is it
We'll be
okay?
waiting. Yes, sir. We'll be waiting, sir.
Okay.
Okay.
Okay. Thank you.
Good morning, one and all. Uh, Please be with us for 5 minutes. We'll be starting in 5 minutes. Good morning, sir. Shall we start, sir?
So good morning, everybody. So yes, sir. Now I am ready to speak on my topic. So
Can
I welcome everybody for my
wait
this
1 minute.
lecture.
One second, sir.
Yeah.
1 second, sir. I will have your introduction.
Yes. Yes.
Good
Okay.
morning, one
Okay.
and all. A warm welcome to everyone for the third session of 3 days FDP program on recent research and innovation in mechanical engineering. First, I would like to introduce the session speaker, Dr. Krishna Murari Pandey. He is professor at the Department of Mechanical Engineering, NIT Silchar, Assam. He is having total experience of 38 years. He has completed PhD from IIT Kanpur in the year 1994, MTech from IIT BHU in 1987, BTech from IIT BHU in Mechanical Engineering in 1980. He is member of Institution of Engineers India Limited, fellow of Journal of Environmental Research and Development, life member of Indian Welding Society, life member of Indian Society of Technical Education, senior member of International Association of Computer Science and Information Technology, Singapore. Also, he has involved in formulation of various academic programs like MTechs in Thermal Power Engineering, Design and Manufacturing, Materials and Manufacturing Technology, CAD/CAM and Automation, and in renewable energy. He has 224 research papers in SCI or Scopus Index database, and he has a total of 450 publications. He, he also authored books like CFD analysis of flow and heat transfer in subchannels of light water reactor, experimental studies on 7 years and batch type rotors, CFD analysis of solid rocket motors, and many more books. it can be seen that he has been very sincere and hardworking researcher throughout his career. Currently, he is working in the area of CFD analysis of combustion phenomena in scramjet engines and CFD analysis of heat transfer in nuclear reactors. Also, he has assessed more than 14 institutions as members of Secretary of NAC. It is our honor, sir, to have you on this session as a speaker, sir. Kindly welcome you, sir, on behalf of management, principal, and Department of Mechanical Engineering of RRIT Bangalore, sir. Welcome, sir, and hand over you the session, sir. Thank you, sir.
Okay, so thank you very much for your nice words. And I remember very well my NAC visit to RR Engineering College, Bangalore. So I will be speaking on the topic numerical investigation on transverse fuel injection, best scramjet combustor for improvement of combustion efficiency. Means in this topic, what we are doing, that we are trying to improve the combustion efficiency for scramjet combustor. Scramjet combustor means supersonic ramjet combustor. And in this, what we do means we ignite the fuel at Mach number 2, and the object moves even at Mach 10, 12, and the object can move even theoretically up to Mach number 25. Like you observe that in this some missiles even they go up to Mach 8 or 10. So this is due to this type of ignition. So my presentation outline will be introduction, then literature review, whatever we have done, then technical challenges and research guide, then research objective, then methodology and validation, and results and discussion, and concluding remarks, then scope of future work and references, and then list of publication. In fact, whatever I am presenting now, actually this is it is the work of my research scholar in the area of scramjet engines. So this is about introduction of this. This you can see the diagram now here. So flow is taking place, and intake and fuel injection, it is injected means from the back side, and there is thrust nozzle from which the from combustor the exhaust gases pass. So in the development of high speed aero vehicle, weight is the major issue in the field of propulsion system. Then to eliminate this problem, a jet engine with absence of oxidizer tank has been recognized because the weight will be light. That is air breathing engines. And air breathing engines complete the thermodynamic cycle by using incoming air from the atmosphere as a oxidizer. Then among them, scramjet is popular, and it is an extension of ramjet and fly at supersonic speed. Supersonic means after Mach number 1, we call the flow supersonic, and after Mach number 5, we call the flow to be hypersonic. And after this, Scramjet acronym is as supersonic combustion ramjet engine, that we call scramjet. Then the engine follows the Brayton cycle, and in the scramjet engines, the atmospheric free stream air enters the combustor at supersonic speed, and the process of mixing and combustion both take place at the same speed. So due to the high speed of incoming air, the residence time is less inside the combustor, which is a cause of means in fact in this type of engine, the flow takes place in millions of seconds, means milliseconds. That then the scramjet engine does not have any moving part, so there is very less way to improve the performance. And after this, the scramjet is composed of 3 basic components. So here in this diagram, we can see the components like converging inlet, and where incoming air is compressed. Then combustor is there, and then the diverging part is there. And combustor where fuel is burnt with atmospheric oxygen to produce heat. And right side you can see the diagram, that is propulsion airframe integrated scramjet. And shock boundary like you can see this thing. Here there is shock trend is there, means there is continuous, you can observe shock wave reflection is there, and the combustion it takes place at mostly at Mach number 2, and how the flame is sustained at this very high speed. This is sustained due to cavities, and this about these cavities I will come at a later part of the story. And this diverging part where the heated air is accelerated to produce thrust. And after that, the fuel injection system. So to develop the to develop the competent combustion chamber at a desired level of speed, a suitable means of fuel injection is required. According to the fuel entrance into the compressed air, high pressure zone can be categorized into three parts, that is parallel, transverse, and combined fuel injection system. So there are three types of injection systems. One is called parallel fuel injection, and where there are less shock waves. Then transverse fuel injection, here there are more shock waves, and one is combined fuel injection system. So these are the three things. So here you can see the air is coming and fuel is coming. Like this, air is coming and fuel is coming from other. This is called parallel fuel injection. And here in the scramjet combustor, air is coming from this direction and fuel is injected like this from this port, means from down to upward. So this is called transverse fuel. And then combined fuel injection, here air and fuel, they are coming parallel as well as transverse injection is there. So this type of numerical analysis we have done. We have not done any experimentation here at NIT Silchar, because at NIT Silchar we are not having experimental facility. And this experimental facility, this is available for up to some Mach number, not at the maximum Mach number. I mean, it is at IIT Madras and IIT Bangalore, it is available. Then mostly in Chinese universities and Australia and USA, mostly universities, they are doing experimental research on these engines. In Germany also this is being done. So introduction. So advantage of, what are the advantage of this scramjet engine? First, let me tell you why, means what is the theory of behind this scramjet engine? Why? Like I move from Silchar to Calcutta. It takes 1 hour from go to Silchar to Calcutta. But if domestic planes, they are with this, they are facilitated with the scramjet engine, one can go from Delhi to USA in 90 minutes only at that high speed. So 90-minute time it will take, and it takes now 15 hours like that. So that flight, it can be, when although it will be very costly, but that travel can be made up to 90 minutes. That is the advantage of scramjet engine. But mostly this is now, these engines, they are used for this war technology. So advantage of this is, this does not have to carry oxygen, and no rotating parts are present. Means basically no engine is there, no rotating parts are present. It is easier to manufacture than a turbojet engine. Means it is, turbojet engines are domestic engines, so it is easier to manufacture. Then has a higher specific impulse change in momentum per unit of propellant than a rocket engine. Then higher speed could mean cheaper access to outer space in the future. Then disadvantages. Disadvantages are, a scramjet cannot produce efficient thrust unless boosted to high speed around Mach 5. Although depending on the design, it could act as a ramjet at low speed. Testing scramjet designs use extremely expensive hypersonic test chambers and expensive launch vehicles, both of which led to a high instrumentation cost, then lack of stealth. Then my next slide. This is the application part. So this is introduction part. So introduction, these are for used for military application, that is application part. Then Scramjet can be used to propel missiles. They are found almost exclusively in missiles where they are boosted to operating speeds by a rocket engine or being attached to another aircraft. Typically, a fighter currently used scramjet propelled missiles are that is number one, X-43 hypersonic cruise missile, which was carried by B-52 carrier plane. Then second one, X-51 hypersonic cruise missile, which was also carried by B-52 carrier plane. Then Russian-Indian BrahMos supersonic cruise missile. Then for civil, there are civil application also. Scramjet speed could reach 15 times the speed of sound. An aircraft using this type of jet engine could dramatically reduce the time when it travels from one place to another, potentially putting any place on Earth within a 90-minute flight. Means we can go from anywhere to anywhere on Earth within 90 minutes if this scramjet engine is used. Then literature review section. So actually many persons, they have worked, and you will see in sciencedirect.com a huge literature about scramjet engines. So I will like to skip this thing because much more work has been done, and even more than 1,000 research papers are available about this scramjet engine, how to improve combustion efficiency, etc. So these are the literature review which is done by my students. So I want to skip this. This is also literature review about this thing. Mostly work is done in China. And then technical challenges and research gap. Why we selected this problem? So what are the technical challenges and research gap? So restart case offers highest mixing efficiency being dominated by relatively large scale vortices. Then the flame holding capacity of the kerosene fuel combustor increases with the increase of the entrance total pressure. The next, uniform mixing and gradually decrease in stagnation pressure loss can be achieved by decreasing the cavity aft wall angle. Then chief among these are how to achieve higher combustion performance in a restricted length at supersonic speed. Then fuel entrenchment strategy there, then lack of combined fuel injection strategy, then explanation of solely parallel and transverse fuel injection strategy, it is missing. So we have done this work. Then we have done some geometrical modification, it is needed, like changes in fuel injector geometry. We can change here the geometry. Then changes in angle of combustor wall. Then created disturbance inside the combustor. So, so chief among these are the problems of how to achieve stable, efficient combustion in a supersonic flow. Still, many issues are not reached up to its desirable effect. Some of the issues are as follows. Efficient fuel injection and mixing is critical to successful development of a hypersonic air-breathing propulsion system. Supersonic velocities within the combustor section limit the time of fuel to mix with the air flow. Because inside the combustor, the velocity is very high, so the time is limited, and surface interaction with the flow create undesirable losses and drag. Length of the combustor is also need that to be reduced by enhancing initial mixing location. Mixing is also mixing is also vary from fuel selection. Then the research objective means what are the objective of the present research work? There are means 5 objectives. That is to investigate the variation of different fuels on combustion performance of scramjet combustor. Then second one, to investigate the effect of variation of inlet boundary condition on combustor performance of a transverse fuel injection scramjet combustor. Then third one is to investigate the effect of variation of fuel injection location on combustion performance of transverse fuel injection based scramjet combustor. The next one is to investigate the variation of transverse fuel injection angle of attack on combustion performance of scramjet combustor. To to investigate the combustor performance with the variation of incoming air angle of attack in combined fuel injection approach. That is the fifth objective of this problem. So methodology and validation, so how we have done that meshing configuration and mesh stability test means grid independent test is done, then turbulence modeling is done, then conversion modeling. Then we have put boundary condition and this residual convergence report, and we have validated this with experimental results of some work done in other country, and that work is done in Germany. So what we do this, how we do the computational modeling, that software details will be given. That is ANSYS Workbench 14.0 Fluent Solver we have used, and program capability 2D planar, 2D axisymmetric, and 3D flows. We can do 3D flows also. And then, in fact, we have done 2D analysis, and in fact, for simulation of Scramjet engines, this large eddy simulation model is the best model, and not this 2D model is not, but we have finished this work for 2D model, but the best model, it is LED model, that is large eddy simulation model. Then we have chosen quadrilateral, triangular, hexagonal, and steady state transient flows, then incompressible or compressible flows, including all speed, then inviscid laminar and turbulent flows, all can be taken. Then ideal or real gases, then chemical species mixing reaction, this including homogeneous and heterogeneous combustion models. So physical model of experimental DLR combustion model, actually we have validated this with this DLR combustion chamber. This work is done in DR. Is expanded through a level nozzle and enters the combustor with a speed of Mach number 2. The combustor has a width of this 0.040 meter and height of 0.050 meter at intercept, and divergence angle of upper chamber wall of 3 degree. This wall can be maximum up to 5 degree. Then wedge safety strut is placed in the combustion chamber. Wedge safety strut means this is the strut, wedge safety strut, and which are located at a distance from this combustor inlet. And the height of the strut is given in meter, and hydrogen is fuel is ejected at Mach number 1 with the help of wedge strut. With this here, we inject the hydrogen fuel at Mach number 1. Here, this is physical model of computational DLR combustion chamber. Here you can see the diagram, and this included angle is 12 degrees, this is 26 mm, so everything for computational analysis, and this divergence angle is 3 degree, and this is 25 mm, so all dimension we can see here. And this work is done by Weidmann ETL, he is from Germany. Then meshing configuration we have done. This meshing configuration we have done like this. So this is done in Fluent. Then grid independent test also we have done. We have increased the number of meshing so that it reaches an stable value. So the mesh modeling is done by using ANSYS, ICM, CFT, and this 3 type of mesh generation is created, that is coarse, moderate, and then very fine. And the generation of grid in network should be in equidistance in the computational model so that the computational time can be reduced. Because this computational time also matters. So error percentage, here we see that with fine, we are having 4.5% error. Whereas with coarse 42% error is there, moderate 19% error is there. Then turbulence modeling analysis. So we have done here. There are so many models, that is KE realizable, error just you can see, KE RNG model, KE standard, and KW K omega SST model. This is having 4% error, so this is chosen, and K omega standard that is 15 error percentage here is more. So we have chosen K omega SST model. Then turbulence modeling. About the turbulence modeling, the SST K omega turbulence model gives suitable similarity and shows good agreement with experimental data with acceptable percentage of uncertainty. The lower valve pressure plot is used to analyze the best suitable turbulence modeling for the present computational case. And here, we have taken single-step chemical reaction model, although multi-step chemical reaction model also can be taken, but the computation time will be very high for that. So these are the boundary conditions. That Mach number in coming year is 2, then static pressure in Pascal, static temperature 350, for fuel 250, density it is given, velocity it is given, then mass fraction also it is given. Then estimate and idea for the flow. Then single step chemical reaction is considered. Then residual convergence report, here it is given. The residual is one of the most fundamental measures of an iterative solution convergence, and it directly quantifies the error in the solution of the system of equation. So in an iterative numerical solution, the residual will never be exactly 0. However, the lower the residual value, the more numerically accurate is the solution. So this is CFD analysis. So we can see here, non-reacting flow case is this experimental. This is the case of non-reacting flow. Here there is no reaction. And this is the case of reacting flow. So these are the experimentation part of Germany. And these are density plot, here it is given. And we can see shock wave reflection or Mach trend. These are obviously visible here. And these are pressure plots. So here also we can see the Mach reflections and other things clearly. So for non-reacting cases, we can see here the pressure distribution. Along the length we can see, and along the velocity also we can see. So non-reacting cases, the pressure, this is the length along the length of the combustor. Here this is velocity, and here again this is velocity, experimental value and numerical value, experimental value and numerical value. So experimental, these are the results, and numerical analysis, we have got this. So we see that this is numerical, and our numerical analysis is completely matching with the experimental values. So that is why our papers are published. Otherwise, unless the validation is there, no paper will be published in any SCI journal. They ask for validation. Then this is reacting case here. You can see here again. This is the experimental thing, the red color, and this is the numerical analysis. And you see that these are matching very clearly. There is cross stream velocity profile and temperature profile also you can see. And about temperature, I will talk that for supersonic engine, this is scramjet engines, the temperature go even up to 4000 degree Kelvin or 3005 degree Kelvin inside the combustion chamber, and this is high F. And in fact, in IC engine, internal combustion engine 4-stroke, we observe that the temperature is around 2500 degrees centigrade, maximum temperature. But here, in the Scramjet engine, the temperature is 3500 degrees centigrade. And like surface of sun, solar, means surface of sun temperature is 5700 degree Kelvin is the temperature of the surface of sun. So here result and discussion is there. So what result we got, that to investigate the present model, numerical investigation is performed with the help of ANSYS 14.0, and it is the analysis is done, and what we got the result. Objective 1, it is to investigate the variation of different fuel on combustion performance of a scramjet combustor. So, performance characteristic analysis of DLR scramjet combustor model, parallel fuel injection, then optimization of incoming air temperature of the DLR scramjet combustor, that is parallel fuel, then impact of different working fuels on the combustion performance of scramjet combustor. We have done this in objective 1. So, in this geometry we have earlier seen for objective 1. So, these are the parameters of analysis. That Mach number of incoming air is 2, and for fuel it is 1. Other parameter also given for numerical analysis. Then this is the performance characteristic analysis of DLR scramjet combustor model. So, shock wave behavior. So, here we can see this is shear layer, this is shear layer, and this is the strut. And here we can see oblique shock waves. And there is a reflection. So the role of the shock wave is to create a sudden change in the property so that the fuel favorably mix with the incoming air and combust and release the desirable heat to create the thrust. As the supersonic vehicle lags behind the residence time inside the combustion chamber, which directly affects the combustion performance. So actually, formation of shock wave actually creates a obstacle for the flow. But shock wave here for combustion process, this helps in combustion process, because after the shock wave, the speed decreases, and due to it decreasing speed, the flame is sustained. Otherwise, the flame will be getting quenched. So here also we can see this thing, Mach number distribution, and the sudden change in Mach number is identified just after formation of oblique shock wave, which reflects the extreme change in flow regime. Actually, after shock wave, the Mach number decreases, and it is responsible due to the formation of recirculation zone. And this implies favorable situation in terms of mixing behavior. And here, this is for pressure distribution behavior, we can see here. And again we can see the pattern, the shock wave reflection, and in compressible flow terms, we call it Mach train, this portion. And this is recirculation zone. This zone is we call recirculation zone, and in case of sudden expansion, this zone is seen. And here, this is the case of upper wall, this is the case of middle section, and this is the case of lower wall. And this takes place along the we are able to see numerically, means what happens inside the combustor. So we can conclude like this, that the generation of heat energy can be attained from high pressure zone. The engine is considered as efficient if the combustor pressure loss would be lesser. The pressure is responsible to accelerate burning rate of species involved. The ignition delay of a mixture of combustible fuel with air is involved around desirable pressure zone. It is observed that rate of combustion is more in the vicinity of the shear mixing layer and wake region compared to the near wall combustion chamber region, and this is due to low velocity. Here is specific distribution behavior, it is seen, and here we can see that the combustion efficiency of standard DLR scramjet combustor model is 92.36% with 100% fuel air mixing efficiency. The mixing completes at the combustor location. So we can see how this combustion takes place in the combustor length, and here combustion efficiency we can see. This is combustion efficiency is increasing, and this goes up to maximum, and this is increasing along the combustor length. And this is also, this is about mixing efficiency. So mixing efficiency, this is also maximum after some length is reached. This is here. Here it is. Here the mixing efficiency is maximum. And here the combustion efficiency is maximum. Means after some portion, it becomes the angle becomes very less. It is almost parallel. Then this is about pressure distribution, and we have analyzed about inlet temperature. Like we have changed the inlet temperature. Like we have taken, this is at 350 K inlet temperature here. This is 400 K. This is 450 K, and this is 500 K. So, and this is pressure distribution behavior, and we can see from these graphs. And this is for parallel fuel injection. So this is about pressure distribution along the length of combustor at both the valve, follow the same pattern due to the change of incoming air temperature. And here the burnt fuel exit temperature ranges from 2000 K to 2500 K. Here the maximum temperature range is 2000 K to 2500 K. Then species distribution behavior we can analyze. We have done the analysis. All the fuel particles have been completely mixed with incoming air, and hence the surplus of here the combustion characteristic is change in air temperature, improve the combustion efficiency in the downstream flow phase. The air temperature 450 K approaches 93.66% combustion efficiency. So if we increase the inlet air temperature, the combustion efficiency, it is going to increase. Because here we can see all the plots. There are 3 plots here. So we have seen that the temperature 450 K, this is giving good results. Then Mark 2, this is combustion performance analysis, and this is about mixing efficiency and combustion efficiency. We are seeing, we can see here the mixing efficiency. So maximum you just see from here, maximum it is taking place at 450 degree K, this is 93.6, and that is maximum. And if we increase more, it is becoming less. Then these are the boundary conditions. This is pressure distribution behavior again. So these are the computational results. And this is the formation of recirculation zone. So you can see the formulation of recirculation zone very well. So the formation of recirculation zone ahead of fuel injector and large size vortices in formation are helpful during mixing, because this recirculation zone, this helps in mixing process. And if the mixing will be good, then the combustion efficiency will be increasing. But however, weak air layer is seen in case of C2H4 and CH4. Means for different fuel, the weak air layer is observed. Then species distribution behavior, we can see. The species distribution behavior is used to identify the consumption of fuel during combustion. Then the central and fuel mass fraction distribution. So surplus of fuel at the exit of combustor in case of hydrocarbon fuel. Then this is combustion characteristics. Here we can see there are 3 fuels we have used for this mixing and this combustion efficiency also. So you just see here for hydrogen, this is the mixing efficiency. For ethylene, this is the mixing efficiency. The red color represents ethylene. And methane, the blue color. And here also combustion efficiency, this is maximum. So maximum with hydrogen actually, the combustion efficiency is maximum with hydrogen. Although for scramjet engines, three fuels are tested mainly, that is hydrogen, ethylene, then methane. But hydrogen is the best fuel for scramjet engines, that I will say. So what are the outcome drawn from objective 1? From objective 1, we have drawn that the distance travel by the fuel and incoming air for the complete mixing is termed as mixing length. Methane fuel has taken shorter combustor length scale, that is 0.026 m to acquire complete mixing. Then, actually, objective 1, this is the best outcome, is maximum combustion efficiency is identified in case of hydrogen as a working fuel with 93.66% with incoming air temperature 450 K. Hence, hydrogen is a better option as a working fuel. Then, objective 2 I taken to investigate the effect of variation of inlet boundary condition on combustion performance of transverse fuel injection scramjet combustor. Then, this introducing wall transverse fuel injection system in DLR model, parallel plus transverse fuel injection system. Then optimization of incoming boundary condition, that is parallel. We have done here parallel plus transverse fuel injection systems. So we can see this is parallel, this is strut, parallel, and this is transverse injection. So shockwave behavior we can see here. This is ready, this is high temperature zone. And shockwave you can see like this. This is start, so no, here this portion you can see this is reflection. Here also this is coming like this, then again. So this comes from basic of compressible flows. And this is for parallel only, and this diagram is parallel plus transverse analysis, both. And shock waves behavior here. Here we can see the recirculation zone. This is recirculation zone. And here also this is the recirculation zone. So what we find here, that the recirculation zone near the parallel fuel entry location is beneficial in terms of mixing. However, it will not be beneficial in regards of pressure recovery. Flow separation can be visualized near the valve fuel injector. Near the valve fuel injector means valve fuel injector is where? It is this portion here. So here we can see flow separation zone. And this is Mach number distribution. This you can see, this is compared parallel and parallel plus transverse. So here, red is parallel plus transverse is red, and only parallel is black. So you can see that parallel plus transverse, here it is increasing. And this is again about pressure distribution behavior. So here also we can see parallel injection, then parallel plus transverse injection. So how they behave, the comparison is done. So this red is for parallel plus transverse. And this black, this is for only for parallel. So we have compared this thing. And this is all about objective 2. So same thing we have done like objective 1. So these things, these figures I want to skip. So ultimately, this is combustion characteristic. So here you can see parallel injection, it is reaching maximum, and this is parallel plus transverse. This is combustion efficiency is not going up to that extent, means combustion efficiency it is decreasing. And here mixing efficiency In parallel plus transverse, the mixing efficiency is increasing. That we can see from this. And this is our pressure distribution behavior. So this is fuel temperature is 250 K, then fuel temperature is 310 K. So we have changed the fuel temperature and we have made the plots with this thing. And this is about combustion efficiency. So combustion efficiency, fuel injection temperature at 310 K, this is having maximum combustion efficiency 90.67. And 250 K, this is 88.97. So out of this, effect of incoming fuel pressure. So that this also we have analyzed. So mostly what outcome we have drawn from objective 2, the outcome means the suitable pressure ratio for the present model is 3. And then maximum combustion efficiency shows 90.67% at 450 K incoming air temperature with 310 K world fuel temperature. And the mixing length is found lesser in case of parallel with transverse fuel injector, is 0.041 mm. Means what we observe that for this dual injection system, fuel means for parallel flow as well as transverse flow, the mixing length it is decreased. Then we are coming up to for objective 3. Objective 3 is to investigate the effect of variation of fuel injection location on combustion performance of transverse fuel injection based on scramjet combustor. Means this is only for transverse, not for parallel. So here we have done computational geometry model, active boundary conditions, effect of variation of wall fuel injection location, outcome drawn from objective 3. You just see. We have taken again this DLR model. So direction of air you can see for objective 3. And this we call transverse injection. This we call parallel injection. This is strut and this is cavity injection. And cavity helps in means the flame to get sustained. So these are the boundary conditions. So here you can see mark number 2, that is incoming air. For fuel it is 1.0. For fuel the transverse injection, mark number 1. Then static pressure, static temperature, all are given. Here you just see the performance characteristics. This is combustor length, this is given. This is combustion efficiency. Combustion efficiency goes from 0 to 100 and it is almost up to 90%, and this is having means this 0.030 m. This is having maximum combustion efficiency. And these are residuals completely converged. So next one we can see here along the variation along the combustion length for maxing efficiency. So for maxing efficiency you just see here this red color, this is maximum mixing efficiency at 0.010 meter. Then these are the fuel species behavior. So based on the residual convergence report, 2 models is chosen to compare the performance characteristics. Both models does not show surplus of hydrogen fuel at the combustion outlet. Means hydrogen is not present at exit. Means all hydrogen it is burned. And wider fuel species distribution at the lower wall along the length of the combustor is visualized in case of 10 m wall fuel injection location. So these are the outcome drawn from objective 3. So objective 3 outcome we have drawn, that is, see, these are the outcomes. The additional shock wave generated ahead of the transverse fuel injector is most likely beneficial to create the streamwise vortices, and this can be impactful towards combustor performance improvement. Then higher combustion efficiency is found in case of 10 mm transverse fuel injection model. Then mixing length is the distance which starts from wedge-shaped strut face to the point at which maximum mixing takes place. The 10 mm wall transverse fuel injector location model takes shorter distance among all other models. Then the 10 mm transverse fuel injector penetrates similar to other model behavior. However, the area covered by the hydrogen mass fraction among all the cases is wider. The overlap area under the curve display clear vision of expansion and distribution of wall fuel injection in the downward direction. So these are the outcomes drawn from objective 3. Then objective 4 comes into picture. The objective 4 we have done, actually this was a PhD problem, and the research scholar, she has submitted PhD on this topic. So the fourth objective of this problem is to investigate the variation of transverse fuel injection, angle of attack on combustion performance of scramjet combustor. So here what we are doing, introducing additional slot at the wall boundary for fuel injection, that is parallel plus transverse fuel injection system, then effect of variation of wall fuel injection angle of attack parallel plus transverse fuel injection system. Actually, so far in my career, I have completed 20 PhD guidance and I have guided 93 for MTech. So, and mostly I have guided some PhD even in manufacturing sciences area and material science area also. And in this is propulsion area of aerospace engineering. Basically, this is not hardcore mechanical engineering. This area belongs to propulsion systems of aerospace engineering. So here again we observe this is strut and this is computational geometry model description. This is objective 4. Here you just see again what we have done. Mark number 2.0, 1.0, 1.0. All actually why we have taken only 2? Because we have validated our numerical results with DLR experiments. So that is why we have taken always in coming year 2 fuel 1 because we want to validate with that experiment. Again, you see introducing additional slot at the wall boundary for fuel injection, parallel plus transverse fuel injection. Means here additional slot is given to analyze the angle of attack of incoming fuel injection. One additional slot has been incorporated at the lower wall, and noticeable combustion performance has been seen by comparing with and without slot fuel injection. So we have seen without slot fuel injection is this. You just see. Without slot is this. And with slot is this green color. So we can see that combustion efficiency increasing by giving slot. And here also we can see. And here although much change is not seen in mixing efficiency, they are overlapping each other. And here you just see effect of variation of wall fuel injection angle of attack, parallel plus transverse fuel injection system. That is objective 4. So what we have done, mixing efficiency, that we have given the angle 15 degree, 30 degree, 45 degree, 60 degree, 90 degree. So 5 we have varied this much. So again you see for combustion efficiency you see this is having, this green color is having maximum. Green color means 90 degree. 90 degree is having maximum combustion efficiency that we are observing. Initially also it is having maximum, and this black 15 degree it is having minimum. So that is our conclusion in this. So H2 mass fraction at lower wall, we can see that hydrogen mass fraction. So it is minimum mass fraction, means hydrogen, no hydrogen is left, all hydrogen is worked during the combustion process. So this is again, you can see here combustor length along what happens. This is 15 degree, 30 degree, 45, 60, 90, this thing. Then this is lower wall fuel injection angle degree, lower wall fuel injection angle degree. So you just see, means objective 4. Objective 4, what we have drawn the conclusion from objective 4, that is the final model selection is based on the mixing length, mixing efficiency and combustion efficiency. Hence the enhanced combustion efficiency is found higher with improved other properties in case of 60 degree angle of transverse fuel injection model, lower wall. Then mixing length is the distance which starts from wedge safety strut face to the face point at which maximum mixing takes place for all the 5 models, that is 15, 30, 45, 60 and 90 degree angle of wall transverse fuel injector. Mixing length is 15 mm, 46 mm, 46, 36 and 36 mm means respectively. So the conclusion is this, that the 60 and 90 degree angle of transverse fuel injection model takes shorter distance. Then by analyzing the model, better expansion and distribution of H2 mass fraction across the length of the combustor has been identified in case of 60 degree angle of transverse fuel injection model. Lower wall. Nevertheless, earlier mixing process has also been identified. Hence, based on this criteria, 60 degree angle of transverse fuel injection is found suitable for further investigation. Means we have to get 60 degrees. That is from objective 4. Then this is our objective 5. To investigate the combustor performance with the variation of incoming air angle of attack in combined fuel injection approach, means computational geometry model description, active boundary condition, effect of variation of incoming air angle, and outcome drawn from objective 5. So you just see, this is dual system, means here parallel injection is also there, this is strut, and this is direction of air, and here fuel is also there, means coming from the slot. This is called transverse injection. So direction of air, it can be changed from here, this is negative, direction of air, this is positive. And again it is same thing, like other, taken in other objective. And these are the performance characteristics. So you see here what we have done. We have taken -5 degree plus 5, -10 plus 10, -15 plus 15 degree, -20 plus 20, -25 plus 20. So we have taken the variation from 5 to 25. And we have drawn conclusion from this, that how the combustion efficiency varies, and we see that you just observe, this is the thing, this color means this plus 25 degree, this is maximum combustion efficiency. And here also again we have done the same thing. Everything for -5 plus 5, -10 plus 10, -15 plus 15, -20 plus 20, -25 plus 25 degree. Again, H2 mass fraction at lower wall. And here we have seen that this mass fraction becomes 0. And this is about angle of attack in degree, and this is mixing length mm. So this is again combustion efficiency with angle of attack in degrees. So we can see the combustion efficiency maximum with angle of attack 94.89, means minus 10. And with minus 20 also, this is maximum combustion efficiency. Then objective done from objective 5 that we are taking here. The additional shock wave generated ahead of the transverse fuel injector is the most likely beneficial to create the stream-wise vortices, and this can be impactful towards combustor performance improvement. One thing I would like to say that those cavities are introduced in the combustion chamber to sustain the flame. Otherwise, at Mach 2, the flame will get quenched. There will be no combustion. So the cavity that helps in sustaining the combustion process. And then higher combustion efficiency is found in case of 60-degree angle of transverse fuel injection model, lower wall. Hence, the parallel fuel injection is utilized with the help of wedge-shaped strut and the wall transverse fuel injection position at an angle of 60 degrees to get maximum benefits in terms of mixing behavior with the addition of overall performance. Then the impact of angle of attack of incoming free stream air is analyzed by utilizing both negative and positive direction of angles. And 10 test model has been analyzed and compared by taking zero angle of attack for incoming air as reference. And the selected test models are -5 plus 5, -10 plus 10, -15 plus 15, -20 plus 20, -25 plus 25 degree angle. The outcome obtained by considering all respect of performance characteristic and flow field characteristic suggests that the suitable angle of attack of incoming air is -20 degree angle. This model does complete mixing with in 20 mm of length scale, and there is no ignition delay has been identified. The model shows 94.89% of combustion efficiency, which can be considered as a very efficient geometrical model for future reference. Then these are the operating conditions, and we have come to the conclusion that maximum what we have achieved out of our numerical results, that 94.89% combustion efficiency is achieved. Then concluding remarks. Concluding remarks of this presentation is the outcome obtained by considering all aspects of performance characteristic and flow. Combined fuel injection is preferable for present selected model instead of only parallel fuel injection case. Then suitable injection location difference is appropriate. Then suitable slot length is 3 mm for transverse fuel injector. Angle of attack of incoming wall fuel is 60 degree, and angle of attack of incoming air is -20 degree. Then the below mentioned work can be considered as a future work. Means actually this research problem is, so future research can be done. Actually, in my view, if this work is done with large edge simulation model, LES model, then we can get much better results. And the future work is that is shifting from steady state to transient state can be an interesting area in the supersonic combustion. That is LES. The large edge simulation modeling can capture more accurately flow field characteristics compared to RANS model. Then the multi-step chemical kinetics need to be explored as a future work. But it will require a huge computer with big space for this thing and with much high RAM. Then there are many commercial software present, and the respective Scramjet model can be analyzed to select the suitable solver. Then these are the references again. And what we have done out of this work presentation, that see, recently we have published one paper that is the numerical investigation of combustion performance of scramjet combustor with variation in angle of attack. It is published in Results in Engineering, that is ESCI journal. That is, it is now published. It is on online in Elsevier. This is Elsevier journal, so this is published. Then this one is International Journal of Thermofluids. Also, we have published one paper, and this also we have published in. This is also published now. That is numerical investigation on combustion performance of various fuels in waste start-based scramjet combustor. That is International Journal of Fluid Mechanics Research. This is ESA. This is also published now by Beagle House. And this is again means the third one is it is published in Energy long ago. That is effect of transverse fuel injection system on combustion efficiency in scramjet combustor. This is published in Energy, volume 18. And this is another paper, the numerical analysis of combustion performance of a waste extract based scramjet combustor. This is published in Thermal Science and Engineering Progress. This is SCIE journal. So this is also published. And we have then this is another also means material today we have published some papers, although material today it is proceeding. Then this International Journal of Research Technology, and one paper we have published in International Journal of Energy Research. That is IJER, that is impact of parametric variation on combustion characteristics of hydrogen fuel, start waste scramjet combustor at supersonic speed. This is published in International Journal of Energy Research long ago, and we have presented papers in SIP 2021 last time. So from SIP 2021, the higher version means the modified version is published in two journals, that is Results in Engineering and this another one is International Journal of Thermofluid. It is not mentioned here. And we have presented two papers in SIP held at University of Sharjah in 2019, and from that we have published in Energy and Thermal Science. So this is all about my presentation. So I thank the audience very much for keeping patience to hear my presentation, and I will be happy to talk more about scramjet engines. Although I work in the area of manufacturing sciences also, and my some keynote speeches they are available on YouTube also. If you search Professor K.M. Pandey academic videos, it is available in as keynote speech. I gave many speeches in international conferences in China. So those 4 videos are available there. So the observers they can see from here also. So again, I thank very much to audience, and I will be happy to get questions, any questions if the audience are having about this. Hello.
Thank you, sir. Thank you for your presentation and valuable time, sir. Now, I request other participants to ask any queries if they have. Hello, sir.
Hello.
I request other participants to ask if they are having any queries.
It looks nobody is having query. I will be very happy to get answers over email or questions over email. I always answer my emails, and I am available at my email ID, so there is no problem. If anybody is having any question, they can ask or they can ask even for some help to me over email if they stuck over some problem in development of scramjet engine. So.
Okay. Sir, good morning, sir. This is. Are you hearing me?
Yes.
This is Sampath Kumaran. Actually, your presentation was excellent on Scramjet engine. They have done a lot of work this area. Here, have you tried any coatings, sir? Any thermal barrier type? Hello? Hello? Hello?
Hello, sir.
It's not
hear you,
audible.
Hello.
Are you hearing me, sir? I don't know, because I didn't
Yes,
get any
yes, I am
response.
hearing.
Yeah. So in this particular range, have you tried any thermal barrier coating, sir, for improved efficiency and all that?
No, actually, we have not used any coating. Means I have not worked on coating. So this presentation has got nothing to do with coating. This is only CFD analysis.
I know that. And not pertaining to this, I'm not asking. Generally, in general, I'm asking.
Yes, I have heard about. I know that coating because
Yeah.
I even review many papers. So even in Scramjet engines, even now they are using powder as fuel. Means in China,
Yeah, it will improve the efficiency also.
powder
No,
as
that's
yes. So powder is also used now.
correct.
Not hydrogen. Even they are using powder for this.
Yeah. You're from NIT Silchar, sir?
Because I have reviewed some paper of energy.
Yeah.
Yes, I am working at NIT Silchar as a professor HG.
Yeah. I think Professor Dr. Vinyas is there.
Retire recently in February 2023.
Yeah, I think one Mr. Dr. Vinyas is there. You know him? I don't know.
Yes. He is there. I know him very well. Yes. Dr.
Yeah. He's not. He's known to me.
Citations are very good, and he is in. Yes.
Yeah,
So,
I know him very well.
very well.
Yeah.
Yes.
I am ex-CPRI, Central Power Research Institute.
At the CPI, I know CPRI.
Yeah.
I have once presented one paper to CPRI also at Delhi.
Okay. Actually, Dr. Parvati, madam, has worked in the area of thermal barrier coatings and engine.
Thank you so much.
Thank you, sir. I will stay in touch with you.
Okay. Thank you so much. Thank you.
Shall we end the meeting, sir?
Yes. So, and if time permits, you can show even my YouTube videos also. It is on material science area, particular not to Scramjet, but material science. There is one video presentation, and it is very good.
Yes, sir.
You can even run that. It is 45 minutes. And it is also, that is very good. So you can use that, and you can use whatever content you want to.
Yes, sir. Kindly.
YouTube. So,
yes, sir. Kindly share that link, sir. We'll share with the participants, sir.
Yes. I am sending that link to you by mail. So
okay, sir. Okay.
So thank you very much for giving me the opportunity to present. I am very happy to be associated with your RR Engineering College because I know very well. I remember that I have gone as a member coordinator of NAG team for the evaluation.
Thank you, sir. Thank you, sir.
Okay, thank you so much. So I am stopping sharing the slide, and I am sending the YouTube link for that. Okay. Thank you so much.
Yes, sir. Thank you, sir.
Okay, thank you.
Okay, now I am ending the session. Next session link will be shared in the WhatsApp group as well as to the mail IDs. Thank you, everyone.